Imagine a world where materials could repair themselves, like a wound healing on its own. This is no longer a scene from a science fiction movie, it's the reality of self-healing materials. These revolutionary materials have the remarkable ability to repair damage autonomously, paving the way for a future of more durable, sustainable, and efficient technologies. The development of self-healing materials marks a paradigm shift in materials science. Inspired by biological systems, scientists have successfully mimicked nature's ability to heal and regenerate. From tiny cracks in your smartphone screen to large fissures in concrete structures, self-healing materials offer a promising solution to enhance product lifespan and reduce waste. The implications of this technology are far-reaching, spanning across various industries, including construction, automotive, electronics, and even healthcare. As we delve deeper into the world of self-healing materials, we will explore their mechanisms, applications, and the transformative impact they are poised to have on our future. Join me as we embark on a journey to unravel the science behind self-healing materials and discover how they are shaping a more sustainable and resilient tomorrow. Self-healing materials achieve their remarkable abilities through a variety of ingenious mechanisms, each inspired by nature's own healing processes. One approach involves embedding microcapsules filled with a healing agent within the material. When damage occurs, these capsules rupture, releasing the healing agent to repair the crack. Another method relies on reversible chemical bonds that can break and reform under specific conditions. When damage occurs, these bonds break, allowing the material to flow and fill the damaged area. Subsequently, the bonds reform, restoring the material's original strength and integrity. Some self-healing materials utilize vascular networks inspired by the human circulatory system. These networks contain a healing agent that is transported to the damaged site, much like blood flowing to a wound. This approach is particularly effective for repairing larger-scale damage. These are just a few examples of the diverse mechanisms employed by self-healing materials. The specific approach used depends on the type of material, the desired application, and the extent of damage it needs to withstand. As research progresses, we can expect even more sophisticated and efficient self-healing mechanisms to emerge. Polymers, the versatile building blocks of countless everyday products, have taken center stage in the development of self-healing materials. Self-healing polymers possess the remarkable ability to repair damage caused by wear and tear, extending their lifespan and reducing the need for replacements. One fascinating example is self-healing polyurethane, a type of plastic commonly used in coatings, foams, and elastomers. Researchers have incorporated microcapsules containing a healing agent into polyurethane, enabling it to repair scratches and cuts autonomously. When a scratch occurs, the microcapsules rupture, releasing the healing agent, which then polymerizes to fill the damaged area. Another promising avenue involves incorporating reversible bonds into the polymer structure. These bonds can break and reform under specific stimuli such as heat or light, allowing the polymer to heal itself multiple times. This approach is particularly advantageous for applications where the material is exposed to repeated stress or damage. The applications of self-healing polymers are vast and varied, ranging from scratch-resistant coatings for cars and electronics to self-repairing seals for pipes and containers. As research progresses, we can anticipate even more innovative applications of these remarkable materials. Concrete, the backbone of our infrastructure, is plagued by a fundamental flaw. It cracks. These cracks can compromise structural integrity, leading to costly repairs and safety concerns. Enter self-healing concrete, a revolutionary material poised to transform the construction industry. It incorporates microcapsules filled with a healing agent. When a crack forms, these microcapsules rupture, releasing the healing agent. This triggers a reaction that seals the crack. The benefits are numerous, extending lifespan and reducing maintenance costs. It enhances safety by preventing crack propagation. From bridges to pavements, the applications are vast and promising. Section 5. Automotive Advancements, Self-Healing Cars. The automotive industry is no stranger to innovation, constantly seeking ways to enhance performance, safety, and sustainability. Self-healing materials are revolutionizing vehicle design and maintenance. Imagine a car that repairs minor scratches on its own, eliminating costly trips to the body shop. Self-healing coatings with microcapsules are making this vision a reality. These coatings repair minor scratches, preserving appearance and protecting from corrosion. Section 6. Electronics, enhancing durability and longevity. In the evolving world of electronics, durability and longevity are paramount. Self-healing materials extend device lifespan and reduce waste. One application is self-healing smartphone screens. These screens repair minor scratches and cracks, especially beneficial for foldable phones, also explored for batteries and capacitors, aiming to prevent performance degradation. The potential of self-healing materials is vast. Future devices will be more durable, long-lasting, and sustainable. Section 7. Environmental impact, a sustainable solution. In an era marked by growing concerns about climate change and resource depletion, the pursuit of sustainable technologies is more critical than ever. Self-healing materials have emerged as a beacon of hope, offering a pathway to reduce waste, conserve resources, and minimize our environmental footprint. The traditional take-make-dispose model of production and consumption has taken a toll on our planet, leading to overflowing landfills and depletion of natural resources. Self-healing materials challenge this linear model by extending the lifespan of products, reducing the need for replacements, and minimizing waste generation. Moreover, the production of self-healing materials often involves less energy and fewer hazardous chemicals compared to conventional materials, further reducing their environmental impact. For instance, self-healing concrete can contribute to a significant reduction in carbon emissions associated with cement production. By embracing self-healing materials, we can transition towards a more circular economy, where products are designed for durability, repairability, and recyclability. This shift will not only reduce our environmental footprint, but also foster innovation and create new economic opportunities. Section 8. Market growth and future trends. The global market for self-healing materials is experiencing exponential growth, driven by increasing demand from various industries seeking sustainable and cost-effective solutions. According to market research, the self-healing materials market is projected to reach billions of dollars in revenue in the coming years. This surge in demand can be attributed to several factors, including growing awareness about sustainability, stringent government regulations promoting eco-friendly solutions, and the increasing adoption of self-healing materials in key industries like construction, automotive, and electronics. The future of self-healing materials is bright, with ongoing research and development paving the way for even more innovative applications. Scientists are exploring new self-healing mechanisms, developing novel materials with enhanced properties, and expanding the range of applications for these remarkable materials. From self-healing roads and bridges to self-repairing airplanes and spacecraft, the possibilities are endless. As the technology matures and costs decrease, we can anticipate self-healing materials becoming ubiquitous, transforming our world and shaping a more sustainable and resilient future. Section 9. Challenges and opportunities in self-healing materials. Self-healing materials hold immense potential, but face challenges in scalability and cost. Production costs are high, limiting widespread adoption. Developing materials for extreme conditions is another hurdle. Yet, the opportunities are vast, especially in bio-inspired materials. These could revolutionize medicine with self-healing implants. Integrating with nanotechnology and AI could lead to intelligent, adaptive materials. Section 10. Ethical considerations and societal impact. As with any transformative technology, the advent of self-healing materials raises important ethical considerations and societal implications that warrant careful examination. One concern is the potential for job displacement, as self-healing materials could automate tasks currently performed by human workers, such as maintenance and repair. Another ethical consideration is the potential for misuse of self-healing materials. For instance, these materials could be used to create more durable and long-lasting weapons, raising concerns about their potential impact on warfare and conflict. Furthermore, the widespread adoption of self-healing materials could lead to a decrease in the demand for raw materials, potentially impacting economies reliant on resource extraction. It is crucial to consider these economic implications and develop strategies to ensure a just and equitable transition. Addressing these ethical considerations requires a multidisciplinary approach involving scientists, engineers, policymakers, and ethicists. By engaging in open dialogue and establishing clear ethical guidelines, we can harness the transformative potential of self-healing materials while mitigating potential risks and ensuring equitable benefits for all. A glimpse into the future. The journey into self-healing materials reveals a future brimming with possibilities. From self-repairing concrete to self-healing smartphone screens, these materials are set to transform industries and enhance sustainability. Imagine a future where buildings repair themselves, cars heal minor scratches, and electronic devices last longer. This is the future self-healing materials are shaping.